Good day, folks. You are back. I'm back. We all back. So now we've got each other's back. So let's do this together. Remember, if you like, subscribe to be reminded every time we post something to get a note that hey, we're here. Please hit on the notifications button as well. But then we are here now to look at the second type of what? Of digital to analog converters, but specifically the BCD types. All right, we looked at the general BCD, what calls the digital or DA, the DAC, DAC. All right, this is a BCD DAC. All right, let me rather say BCD DAC, digital to analog converter, because binary coded decimal digital analog converters. We looked at the general case. This is our general case here. The general case of the what? Of the digital to analog converter was basically a what? Based on the summing amplifier. We should not forget that this is a what? This is our summing amplifier. So everything is coming from him, summing amplifier. All right. So we should not forget that this is where we stepped out of. We're still busy with the operational amplifiers. We're still busy with the what? With the summing amplifier. But now we're looking at the what? The BCD deck. We looked at the one type. The one type was. Okay. Before I do this, the one type that we had was this type. We had this type. This was a specific example chosen so that our step was 1 volt each. 0 meant 0, 1, 0, 0, 0, 1 meant 1, 0, 0, 1, 0 meant 2, so it was 1 step each. Let me explain steps. Maybe I'm bringing in a new concept here that I probably didn't delve into previously. Now, what is a step? Let's look at these switches. Let's suppose we have 0, 0, 0, and 0. This would mean obviously no currents anywhere, so there'll be no, the sum of the total current will be 0, so the output will be 0. So 0, 0, 0, 0 gives us 0 volts. All right, let's turn that last one there to a 1. Okay, what does it mean? It means our V out is given by what? Our V out is given by the 5 volt. Okay, now from this 5 volt, what then happens is what? What then happens from this 5 volt is that I shouldn't have said 5 volt. I should have said minus RF. This 5 volt here, I should put it inside here, is supposed to be, this is I, voltage is resistance times current, the current through the what? Through the 100K. So this 5 volts should be used to calculate that current through the 1K. And but our RF, what is it? We have a value for RF, therefore I can go ahead and say, since it's given right there, it is what? It is 20K. As you can see from that, the K and the K goes 20 times 5 is 100, 100 divided by 100, that is minus 1 volt. So we have therefore on good authority that this here is going to be 1 volt. Let's try this 1 0 instead, which we know is 0 0 1 0 is the equivalent of 2. Okay, now let's see. We have here the same thing, except that is 20K. Yes, the feedback doesn't change, the voltage doesn't change, all you change is the different switch, therefore the resistance changes. It is instead of 100K it is 50K, because we are using that switch there. The one closes this switch, so we are using 50K. Our current is through the 50K, 5 volts with 50K, 5 volts with 50K. Our feedback is 20. What do we have now? We have 20 times 5 is still 100. That's 100K. 100K V divided by 50K. The K for K, 100 divided by 50 is 2. So we've gone up by 1 step. We've gone to 2 volts. Oh, it's minus. It's negative, by the way. Okay, it's negative. Why? Inverting amplifier. All right. So we go on and say, what if we go on and say 1 1? 1 1. What do we have? We have a different scenario now where we have, yes, our 20k VK. There is our 20k. It's already there, our 20k, but our current one is going to be 5 volts divided by 100k. 5 volts divided by 100k plus these two currents are adding up there. That will be 5 volts divided by 50k. 5 volts divided by 50k. By now we should know this is 100k divided by 100k. That's 1 minus 1 plus that one there is 100k divided by 50k, which is 2, which is minus 3 volts. So that's minus 3 volts. So what do you notice here? I'll do the last one so that you can see each step we are going up by minus 3 volts. Each step we are going up by a voltage. So this is seeming, let's prove it with the last one. 0 1 0 0 0 1 0 0 will be what? Minus, yes, but what do we have? We have, oh, it's 0 1 0 0. So what do we have? 0 1 0 0 0 1 0 0. So only this switch closes is the 5 volt with the 25k. So we've got minus 20k our feedback into 5 volts with the 25k. As you can see, this 100k V over 25k, that will be 100 divided by 25 is going to be 4V. Now, as you can see, oh, we forgot, of course, that it's inverting. All right, this will be minus 4 volts. So each increment or step, increment or step is equal to minus 1 volt. Okay, so we are incrementing by 1 volt each time. So I don't know, this is the concept of what, of the way I've chosen my values. I've designed them so that every step is a volt. All right, it can be chosen different and then it can be manipulated later to see what it means, but I've chosen a scenario that is straightforward where 1 volt goes with every step is a volt. All right, so you may have lesser steps, you may have greater steps, well, according to your desire and what you intend to do. Just bear in mind that you may not make this resistor extensively big, because if this resistor becomes too big, then it will overload your what? It will overload your, it will saturate our operational amplifier. All right, so now what do we then go and do? We then go on and say, all right, let's go and say, if we understand this, let's go to the scenario that we had before. We had our, I wanted to explain the steps because people might meet questions that talk about steps. I've got a few already myself in my classes, so I wanted to say, let me deal with the steps. I seem to have neglected them. Now let's go on and say, another scenario could have been, no, the previous scenario that we dealt with of a deck was essentially, I have to ungroup this. Ungroup, I don't want that writing there. Okay, now I want to remove this here. Okay, I don't want that. Now I want this to be we want to turn this into a what? Into a, let me rather change this altogether. Let me change this altogether. Let me remove this for now. I want to do this a little bit. I want to make this a little bit longer and put my amp a little isolated from just to give it a little bit of space, physical space. That's it. That's supposed to be straight lines. This is supposed to be a nice neat triangle. All right, so this here I want to have mine. Okay, this is supposed to be a nice beautiful triangle, so excuse my bad writing with the equipment that I'm using here. So I want to have my feedback a little from the circuit diagram, at least a little isolated, so I don't have traffic. All right, now what then happens is I want this set repeated. I want this set repeated. Okay, I want this set repeated, and I'm going to say no. Not that mampara way, let's rather do this. Recloning, have another set up there. Let me put it down here so that we can have this a little bit down. Okay, what I want to do here is I want to have this one here cloned. I want to bring it here as well. I want to have 3 of them. What am I doing here? Let me address what I'm doing. I'm going back to our previous scenario, cancel running. Also, I wanted to say ungroup, and then okay, I also want to ungroup this. Okay, so now what I want to do is I want to I'll explain. Let me finish what I'm doing first. Was talking and I think sort of takes the concentration. Now I want to join this and join that. Okay, previously we said when I want, look, let's look at the formula V is equal to IR. This is about currents that are supposed to go through RF. RF being equal to 20, out of our design now is 20K. We want the current, if the voltage is going to be constant, we want the current to be the same. So I want to maintain, so instead of this probably, let me say I is equal to V over R. Now, to maintain I have 2 ways of maintaining I. One way of maintaining I is if I reduce the voltage. Now, if I reduce the voltage, I must also reduce the resistance. If I want I to be constant, for I to be constant, if I reduce the voltage, let's make an example. Let's say I've got 1 amp from 1 volt and 1 ohm. Now I want to maintain this, but I want to reduce the voltage to 0.5. Then that ohm must go on to 0.5 as well. Then it stays as 1. So if I reduce the voltage, I must also reduce the what? The resistance if I intend to maintain the current. So this whole episode here is going to be about what? It's going to be about reducing the what? Maintaining the current. All right. And when we intend to increase the current, we'll explain why. But I want to, oh, okay, wrong ruler, wrong instrument. Now, based on this formula here, let me rather take this formula and let me rather change this formula because my interest is I. Let me have I is equal to V over R. Let's bear this in mind. Now, that being Bonnie in mind, let's go on and say, for this scenario here, I don't want to be showing a lot of voltages like this. In the previous scenario, we said, that one is still grouped. So let's go and ungroup it because it's going to keep giving us a headache. Ungroup. Let's see, ungroup. Let's see, now it's not grouped. Now what I want to do is I want to remove these different what call the sources here, because all of them come from the one source. One source. Okay, so all of them are 5 volt sources. Now, however, if I do this, there is no way that this is going to be what? A BCD converter. We say that the resistances must change. The ratio of resistances must stay the same between a set. This is set 1. This is set 2. This is set 3. Now what I want to do is I want to have my units here. Okay, I want to have my tens here, and I want to have my my tens here. So I want to show how we go up and how we go down. All right, to go further up, we'll still follow the same format. All right, to go from units to tens, I need to increase by a factor of 10. So if I increase the current by 10, I will increase the what? The magnitude of the voltage by 10 as well. So if I increase by a factor of 10, I'm going into the tens field, obviously. If I reduce from the units by tens, I'm going into tens. So if I reduce my currents by tens, then it means that what? I need to, if I reduce my currents by tens, it means my voltages will follow suit. Okay, so if my voltages follow suit, then it means my voltages will be in the what? In the 10 less factor. The 10 less factor will be obviously the tens compared to the units, if you're talking from the units. Now, let's go and say, so for me to achieve this is currents. This is currents. Okay, I'm reducing the currents here. There's two ways of me doing this. We have looked at one already. The one was, we simply said, I can't use the same resistances if I want the currents to be less. We've said let's factor in 10, and we've said this was our previous scenario. I want you to relate with what's going to happen next so that you understand going forward. So now, we don't really have values here. I'll come with values later. I'll probably change values later. I might not change all of them, but I'll change some values later. All right, I'll change some values later. Let me not have values for now. I don't want to have values for now. Okay, so let's say what we have now is a scenario where the one scenario you want to reduce the currents by 10, by a factor of 10. The other scenario you want to increase our currents by a factor of 10. Thus, reducing the what? The voltage is by 10. If I want to reduce, if I reduce this by 10, I'm obviously also what? Reducing the voltage by 10. The resistors are going to do this for us. So if I want to reduce, there's one way of doing this, reducing the currents. I can reduce the currents by reducing the what? By increasing the voltages. To reduce current, I can increase the voltage. The resistance. What am I saying? By increasing the resistances. So to reduce current, I can increase the resistance. But also, to reduce current, I can reduce voltage. So I will either to reduce the currents, either reduce voltage or increase resistance. Okay, that's how we can achieve that part. Obviously, we do nothing here, but here also either increase voltage or reduce resistance. So we're going to see how we get by a factor of 10. The factor doesn't change. The factor is 10. By a factor of 10 in each case, we either going to reduce the voltage or increase the what? Increase the resistance to reduce the current, or we are going to increase the voltage or reduce the resistance to increase the current. So this is what we're going to do, but we're going to do this by factors of 10. So previously, in our previous example, we increased the resistances. So when they say this here becomes 1 meg, that there becomes half a meg, which is what? This is 1 meg, that is 10 times this. This one here is going to be half a meg, which is 500, because it's factor of 2. These sets are factors of 2, don't change. Within here, the factors of 2, the factors don't change. This is going to be half of it, which is 500k. That is going to be half of it, which is 250k. Half of it, which is 125k. Yes, I'm right there. All right. If you can see, this is basically, if you look at this set, it's 10 times the units. All right. This here is, we've increased the what? The resistance is here is 10 times the unit. But internally, the factor of 2 does not change. For every set of 4, why 4? BCD needs 4. I mean, we've got BCD, the biggest being 91001. So BCD needs 4 digits. So we need to have, remember it's 8421. So this is 8421 BCD. So you need 1 for the 8, 1 for the 4, 1 for the 2, and 1 for the 1. So now, if you go on here, same thing. This is another set. This is set A. This is set A, which is our tens in this case. We increase the resistance, therefore we reduce the current. All right. So this is set B, which is our units as they are. Set B, and this is set C. Okay. So what do we do here? For this one here, we reduce the resistance. So what do? We say by a factor of what? A factor of 10. So this is going to be 10k. It was 100k, so it's going to go to 10k, and this is going to be 5k, because now internally the factor is half. For every set, the factor is half. So this is going to be 2.5, 2.5k, and 1.25k. And this is what we did previously, and this worked perfectly. All right, our previous work. That's why I'm saying people must actually what call this, to not miss any work. People must subscribe so that they don't miss any of this work. Okay, and please, if you like, please do like, because this is how we know we are being appreciated. And then now, if we look at this now, you can see that we've achieved, this is what we did before, and we did a calculation on this, and we saw how this worked perfectly. We also used step 1 voltage steps or increments, so you saw that it worked perfectly. Now what we then do is we have the alternative B, which is voltages, meaning we are going to deal with the voltages. So this was the one case, we worked it out, it was fine. Now we go and say that was one way of doing it. A second way of doing it, which is actually today more of today's work, we say, okay, how about we do not give them one voltage, but rather different voltages. But we can't, we do the one or the other. We said either reduce the voltage or increase the resistance, or not both. Not reduce the voltage and increase the resistance. No, reduce the voltage, increase the voltage in this case, or reduce resistance, not both. So now it means we are going to say, but then how do we then have? So I'm going to go. I want to maintain a situation where I have my increments are 1, my step is 1. I don't want to change that. So now if I'm going to change my voltage, I have to change the resistance values. So what we're going to do is we are going to start with something like 20k here, and then this is going to be, this doesn't change. The relationship within a set does not change. So this is going to be half of it 10k, half of it 5k, half of it 2.5k, 2.5k. Now we said, let's see if this works. Let's take a value here, 0, 0, 0. We know there will be no currents to add here. The output current will be 0. Therefore, 0, 0, 0 will give us 0. 0 volts. Now we change that one to 1. And we know now we are going to have a V out is equal to RF minus RF by, we only have 1. The voltage here, I didn't put a voltage. I want to use 1 volt here. All right. The voltage there is 1, and the resistance is 20k. What do we have? 20k over 20k. We have minus 1 volt there, minus 1 volt. So I'm already seeing that I'm going where I want. I wanted to maintain my one V step, my 1 V increment, and I'm getting that. Let's try a second one, and if it works, we know we are happy. Let's go and say, what if it was 2? So this here is going to be 1, 0. So what changes there is the resistance that we are using is not 20k, it is 10k. So with 10k minus 20k and 10k, 10k resistance is going to give us a ratio of 2. So that is minus 2. 20 divided by 10 is 2. So this is the 2 gives us a 2. Alright, let's have minus 2. I will bet that because it's 1 step increments, so it need to be 1 step increment up to 7. Let me just go to 7 and see. If it gives me 7, I know that this is working perfectly. Let's have 1, 1, 1. And if it's 1, 1, 1, we know that this is no longer true. This is no longer true. So what are we going to do? We are going to say it's minus 20k. And then inside there is a 1. The supply is 1 volt in each case. 1 volt over 20k in this case. We know that's 1 already, plus 1 volt over 10k. 1 volt the input over 10k. We know that's 20k over that, that's 2. And then that one there is 1 volt over 5k. 1 volt over 5k. And this is 20k, 20k, that's 1 minus 1 plus 20k divided by 10k, that's 2 plus 20k divided by 5k, that's 4. And yes, this is minus 7. So we know that 7 is the second step. So all the way up to 7 there, it gave us 1, 1, 1. It gave us minus 7 volts. So we are happy that this configuration here will give us one step. I wanted one step. So first of all, I've got my one step. So I'm happy that my output is working out correctly with this value. Mara, what I want to do now? What I want to do now is therefore saying I'm not going to play with resistance this time. I'm going to play with voltage. So I'm going to come there and say, no, not resistance. We don't change our resistance. Our resistance is going to be the same. The one method was where we change the resistors. The other method is where we keep our resistors the same. 20k, 10k, 5k, 2.5k, 20k, 10k. You can use other values. This is my example. 5k and 2.5k. Okay, so now what then happens is we are going to then say, we already know this, right? Oh God, let me rather not remove it because you tend to remove things and then need them. Let's rather move it to the side as a reminder for some. Maybe now you are listening, you're going to take your notes later. A reminder for some, let's put it there and say, in this stage, we are doing this, either doing that, either the first instance where we change the resistances, or the second instance now where we're going to change the voltages. So also here we're going to say, what is T there? Tens. Oh, that was when I had tens there. Oh, okay, so it goes together. So it goes together. This is the tens. All right. So what do? We say, all right. Now, we say, however, we cannot have one voltage. All right. What do? We are going to say each one its own voltage. But our factor does not change. Our factors were tens for the resistors. Our factor for the voltage is also going to be tens. So here we increase the voltage, so it's going to be 10 times because our factor is 10. Okay, so this is going to be 10V. Here we reduce because our factor is what? Is 10, but it's a tenth. So we go and say this divided by 10, 0.1. Yes, so this can be achieved by varying the resistors, making sure that the sets of resistors have a factor of 10. That factor of 10 can either be the resistance factor or it can be the voltage factor. You have to be very careful which one you've gone for. So there is one way of doing it. Constant resistance values, different voltages, or constant resistances, different voltages. What did I say? Constant resistor values, different voltages. And then I went on to say the same thing. All right, okay. I'm getting tired maybe. So it's either that or it's constant voltage and different resistances. All right, that is what you must be careful about. So now we go on and say, does it work? Okay, do we have to repeat this? We know we worked this out too. This set B gave us 7 volts. So we know that one gave us 7 volts. It can't change now. What will change it? Now let's go and work out the voltage V for set A. Let's call this V for set B. Okay, V for set A is simply going to be, let's say we have there 0, 1, 0, 1. Okay, let's see. You have your RF being 20k into your voltage being 0.1. We have two of them on the 20k, and you have another one on the 5k, 0.1 volts supplied to the 5k. And what do you see? You have yourself there. This here is going to be 0.1. That part is 0.1. Or remember, it's minus. Our output is minus. Remember, it's inverting type. It's an inverting type. So it's minus that plus, if you look at this here, this is 5k into that. That is what? That is 4. Right. So 4 times 0.1 is 0.4. And you have yourself our minus 0.5 volts there. Right. And you can see this gives us 5. This is 0.101, which is 5. Let's go and say this part here, we've already looked at it. That was when you started. You can go back and rewind and look at it if you can't remember how. Now we've got 10 volts here. What we do, we go on and say our V for the set C is equal to, we didn't give a figure, let's say we gave it, remember it's BCD, so it can't be higher than 9. So this can be 1, 0, 0. Let's make it that, because now everything else will be boring. Let's go ahead and say we have an RF of, and by the way, VB, not D, is minus that. All right. Then we have an RF of minus 20k into the first current is 10 volts divided by 20k, because the 1 is on the 20k, plus we have another 1 on the 2.5k. So it's 10 volt and 2.5k. Okay. Now, if you look at this, this is going to give us, if this is that plus that, okay, sorry, this divided by that is going to be 1, that will be minus 10 plus, and if you look at this here, this is going to be 2.5 into that, that is going to be 8. 8 times 10 is going to be 80. Together we have minus 90 volts. Okay, so is this the tens? Yes. 1001 is 9, 9 tens is 90. This was units, 0111 units is going to give us 7. And then this here is the comma site. This is going to be 0101, and this is what? Comma 5. So together, therefore, V out in total, V out equals to minus 90 minus 7 minus 0.5, which together is 97.5, 97.5 volts. Okay, it's a negative because of the inverter. Now let's see, what do we have? We have 1, 0, 0, 1. We have 0, 1, 1, 1, and we have comma 0, 1, 0, 1. And if you do BCD, that is 9, that is 7, and that's a comma in its place, and this here is 5, which is exactly what we have there. Therefore, our DAC, our deck, works perfectly. The BCD deck, digital to analog converter, it works perfectly. And remember that it all started with a summing amplifier. Summing amplifier. Okay, so this has been summed up pretty decently. I hope we all happy. I don't know what I've explained the steps. I've shown you how you can either vary the what? Vary the resistance, or vary the what? Or vary the voltage. And I've done in the previous session, I did the one with the what? With the resistance, where we increased the resistance and reduced it depending on whether we're going up or down respectively. And then, or now in this session, we did our what? We did our last option, which is to what? Which is to increase the volt, to change the voltage rather. And hopefully you like this. If you did like it, for sure, encourage us to do more for you, and we will be definitely be dropping more for those few that like us. So we'll definitely be dropping more. So make sure you are subscribed, so you know exactly when that is. And then thank you so much. Till we meet again, let's keep doing this. Ciao.